Today we will study about a string search algorithm called Rabin Karp algorithm. So let us see what is the problem statement. So first we are given a text. In a string search problem we are given a text and then we are also given one pattern, and our job is to find all occurrences of pattern P in the given text T. So if you are asked to do this, that find ABCA in this, all the occurrences of ABCA in this text, how you will do it? You will start looking it manually. So whenever you see A, you stop because the first character is A. Then you see whether the next three characters are BCA or not. So here it's AA. So we go to next one. We search ABCA. So we found a match and we continue this way. So we will find one here again and one towards the end. So this is called naive approach. So what we are doing here, we are first sliding P against T. So you can keep these two aligned and just compare character by character. If you find mismatch at any point of time, we slide it next by one character and again start the match. And we keep on doing till we reach the end. If we have to find just one occurrence, we will break or stop whenever we find the first occurrence. But here we have to find all the occurrences. So this is the naive approach. So what can be the time complexity? So we slide it. So sliding one at a time. So we will reach end exactly in n minus m steps, because we will not move beyond this last four characters. This will be the last window. So this is linear. So if the text length is n for New York, and pattern length is m for Moscow, then the time of complexity will be m cross n, because we slide it once and then in the worst case we may compare m characters and we are sliding approximately n times, so mn time, so O of mn. So this is the naive approach, but this can be very bad if m cross n is very large. So we will try to improve on it. So that's where we will use Rabin Karp, which will try to reduce this time complexity from O mn to O of m plus n on average case and in general cases. But there is still one worst case, and we will see that later. But in most of the practical cases, it will be O of m plus n, assuming how we calculate hash. In this case we will use a rolling hash. So we will see we can calculate the hash of a window in constant time. So now let's see the Rabin Karp approach. So we slide P against T one step at a time, same as the naive approach. But what differently we do? Instead of matching P against T, so matching P against T means comparing all the characters. So it can be O of m time in naive way, but here we are comparing a value. Hash of P is a value, integral value. Hash of T is also a integral value. So here T does not mean hash of the complete text, just the current window in the text. So comparing that is constant time. So provided if we can update the hash of next window from the previous hash. So if we have hash of 4 characters and then we have to move it by one step, you will notice that just one character has changed. So these 3 characters will remain in the next window also. First character will go away and one more character will come. So we have to define our hash function in such a way that it is sum of character multiplied by some constant plus next character multiplied by some constant, so that we have a value. In the next step we will subtract one value and we will add one value. So this we will call rolling hash, and we will see how we will calculate that. So once we match, are we sure that if the hash matches, then the pattern and text is also same? No, it does not. If your hash function is very good, then the chances that two different strings will have a similar hash will be less, but it will not be 0. If you have a really poor hash function, which we will see an example, then there will be many more collisions. So just matching of hash does not mean the pattern and text has matched. So once there is a match, if there is no match, there is no chance of strings matching. But if the hashes match, then there is a chance of match. So next will be, if there is a match, do character by character match. So on average case, we will have to do it a few times. Let's say there are 5 occurrences of this pattern in the text, and let's say hash is matched 6 times. So one time it was a false positive. So on average it will be 5 times m plus n. Now we have to talk about hash function. A lot of it depends on the hash function. The main logic lies here. So let's say we have a text C1, C2, C3 all the way up to Cm. So there are m characters in this text, and C1, C2, these denotes the characters. So we will define hash function in this way. So C1 plus C2 times x. So x is some multiplier which we will see. Generally we take some prime number. So C1 is the character. So by character we mean the ASCII value of this character. So for example, ASCII value of capital A is 65, small a it's 97, small b it's 98, and so on. So first character, then second character times C2x plus C3x square all the way up to Cm x m minus 1. And we will be taking modulo some number, because this can really become very big and it can overflow, and after overflow you may not get the desired result. So we keep taking modulo some quantity so that it's within some range. This is same as this. Exactly this is not same as this, but let's say we have this text. Nothing stops us from taking C1. Actually there is a mistake here. This should be C1 next to 1. This is fine. Then it should be Cm. So let me correct it. So this is Cm, the last one. This is Cm minus 1. This is Cm minus 2. So let's forget it. So instead of multiplying here x0 then x, we have done it in just reverse order. So so this is as good hash function as this one, and we can use them in different scenarios. So let's say our window is, we are sliding window from left to right, then the second one would be more efficient, calculating it in constant time from the previous hash. And if we are sliding the window from right to left, so for finding the pattern, nothing stops us from sliding the window from right to left. So in that case, we will go with the first one. So we will see why it is easier to use the second version when we are sliding from left to right. Left to right sliding window is quite natural, and we will use that. Next, let's take an example. So we have ABCA, a concrete example. This is the text for which we want to calculate the hash function. So again, I had copied it. So again, this is a mistake. So first character, so m is here 4. There are 4 characters in this text for which we are calculating the hash. So first character multiplied by 1 less than m. So you see x m minus 1. Then b x square cx plus a. So now put some value of x. Let's say any prime number, let's say 11. And a, b, c, a will be their ASCII values 65, 66, 67, and again 65, and modulo q. So in this case there will not be any overflow, but let's say q is some value, let's say 128 or some value. So this is how we can calculate the hash function. Now let's say we calculated the hash function of some window and we slide by one step. How we will update this hash function in the constant time? Because if we are not able to update the hash function in constant time, then our expectation of O m plus n will not be valid. So we have to update it. So ABCA is the window for which we have already calculated the hash. Next, we slide it by one step. Now it's BCAD. So 3 characters remain same. 1 character added, 1 character subtracted. So new hash function will be bx cube plus cx square plus ax plus d. Now if you compare these two, h and h new, you will see that Here last three terms are bx square plus cx plus a, and here you see that first three terms will be similar, bx cube plus cx square plus ax. Only difference is that one x is extra in all of these three. So if you multiply the last three terms by x, you will exactly get the first three terms of the h new. So what we did here, we subtracted the first value ax cube. So from h subtract the first value. First value will be always the character that we just skipped multiplied by x raised to the power m minus 1. So we subtract that value h minus ax cube, that is constant time. Then whatever is remaining, multiply that with x. So we get the first three terms, and after that just add the newly entered character d. So there are three operations, one subtraction, one multiplication, and then one addition, and of course modulo operation in the end. So it will be independent of the size of pattern. So we can, given h, we can calculate h new in constant time, O of 1 time. So this is what we are doing here. I have not written modulo q, so that is understood. You have to add that while writing the code. Now we know how to update it. Now let's see Rabin Karp in action. So we have one text, we have one pattern, and let's define a simple hash function, not the one we talked, but for simplicity, let's say we have a hash function where we just sum the ASCII values, no more calculation. Of course, this is not a good hash function, and even for simplicity, let's skip the ASCII value also. We will just take a as 1 instead of 65, 66. It will be even simpler, 1, 2, 3, and so on. Then the hash of this will be 1 plus 2 plus 3 plus 1. 1 for A, 2 for B, 3 for C, and 1 for A. So it's 7. Now we calculate the first 4 characters hash, and it will be also 7, because we add 1 plus 1 plus 2 plus 3. So straight away you see that hashes match, but the character does not match. The order is changed. Now if there is a match, we do character by character match, but it will not match. Now let's move to next window. Again it's 7, but this time there is a match. For the next case it will be again 7, but again mismatch. Then next window will be CAA AAA, and this time it will be 6. So hash does not match, no need to compare. Next it will be AAA B, and this time it's 5, again does not match 7, so no need to compare. Then again there is a match, but character by character shows mismatch. So of course this was a very bad hash function. There were many more collisions. In our hash function that we just discussed, there will be very rare matches like this. Of course this was very poor, because just if we change the order, it will change. So once hash match, do character by character match to eliminate false positives. Now we know how Rabin Karp algorithm work. Let's see in our code. So this is the text, this is pattern, and we have to define a function Rabin Karp which takes text and pattern and returns or prints all the occurrences of P in T. So first let's M denote the length of pattern. Then we will calculate the length of text. So n is the length of text. Then q is the value we were talking about, modulo, whatever we were taking modulo. And then we had one multiplier, if you remember. So we will take some prime value. Let's take a small value for simplicity, for easy calculations. If we need to verify, we can verify manually also. So this is the multiplier, x, x1, x2, x cube. So this is the modulo q term, and these x's are the multiplier which we have just written. So I am writing the same variable name so that you remember. Now what we did, we subtracted a x raised to the power m minus 1, the first character raised to the power x multiplied by m minus 1, and then added d. So we need x raised to the power m minus 1, and we will always need that only, no other power of x whenever we are subtracting. So let's denote it by x underscore m. Actually it should be m minus 1, but let's say it's x underscore m. So this will be used for next hash. We have to subtract this quantity multiplied by the character which is going out of window. So we can calculate this xm. We have to multiply x m minus 1 times, and we will keep taking modulo so that it remains within some range. And now let's calculate the hash values of pattern. For the pattern is not changing, so we will need to calculate the hash value just once. For the text we will be updating. So let's calculate the first window of the text and hash of pattern, and let's capture them in hash underscore p for hash of pattern and hash underscore t for hash of current window in the text. So initially we are just calculating the hash of pattern and the first window of the text. Since both are of length m and similar calculation is required, we can club them together under one loop. So what we do, we multiply by x, add the current character and take modulo. In the next time when we multiply this whole thing by x, you will see that whatever was x here becomes x square, and so on all the way up to x to the power m minus 1. Similarly for text. Now we have first window and hash of first window of text and hash of the pattern. Now we will start matching and updating the hash within one loop. So we will start from 0th index, 0, I equal to 0, and we will not go till n, but we will stop at the start of last window, and last window will stop at n minus m. So we will be checking till it's less than n minus m plus 1. For example, if n is 3, let's say text size is 3 and pattern is of size 2. So there will be just one slide, compare in the beginning and then slide by one step. So the starting index for that will be 1. So you can see 3 minus 2 is 1, and it should be 1 times only. So that's why, since we are taking less than, we are adding plus 1. If you are taking less than equal to, you can remove plus 1. So if the current window hash in the text matches with hash of pattern, there is a possibility of match. There is a chance of match. There is a high chance of match if your hash function does not, for your hash function there are not multiple collisions, but if your hash function is poor, then there is a kind of 50-50 chance. In our case it will be very high chance. There are very less chances of collision. Now we will do character by character match to make sure that we don't include any false positive. So there will be, in the worst case, m comparisons. So this loop goes from 0 to m minus 1, and p of j, if at any point of time we find mismatch, then we break. No need to compare further, we found a mismatch. But if we did not find any mismatch in this complete loop, then that means there was a match. So we will return match found at index whatever is I. but this will currently execute irrespective of break or not. It will break and it will print. So we will keep a flag found and we will make it false just before break. So bool found is true by default. If this break condition did not hit, then it will remain true, otherwise we will make it false, and we will print this match found only if found is true. So now this is for when the hashes matched. We have other condition, hashes does not match, then we have to calculate the hash of next window, but we have to make sure that this was not the last window. If this was already the last window and we did not find any match, then no need to compare further, no need to calculate the next hash. We have already compared the hashes for the last window. So if it was not the last window, then continue hash computation. So what is the check for that? If I is exactly equal to n minus 1, then this is the last window. So we have to continue this only if I is less than n minus m. So hash t, and you know how to calculate hash t. So whatever was old hash t minus, remember that x raised to the power m minus 1 multiplied by the character that just went, the leftmost character in the previous window. So here a went out of scope, out of window, a multiplied by x raised to the power m minus 1. So this is what we have done here, and now we multiply the whole thing with x, the same multiplier, and then add d, the new character. So multiply whole thing with x. So we are just following what we saw in the explanation. If at any point of time you are lost, go back to the slides, see how we calculated it, and then write your code accordingly. Then we add the newly introduced character, which is t of I plus m, and then don't forget to take the modulo q at each step. And one thing you can notice is that this hash t minus ti multiplied by x raised to the power m minus 1, this can be negative, because this x raised to the power m minus 1 can be a large quantity. So minus this, it can take this value negative, and take modulo of negative, it will be negative. So if it's less than 0, just add q, because modulo q, it will not be less than minus q. So adding q should make it positive, and we are done. So let's compile this now, and let's run this. And it found 3 matches at index 1, that is second character, 6, that is 7th character, and 17th character, 1, 6 and 16. And you see in this, at the starting second character, there is a match. If I highlight it, you can see it has the ID is already highlighted the others. So this is denoting the first one, this 6 is denoting this second window, and then the third one you can see starting at 16th or 17th character. So it had found all the 3 occurrences. Now in the beginning of the lesson, I had promised you that I will show you some worst case scenario where it may not be order m plus n. So this is the worst case typically. So if all the characters are same and the pattern is this one, AAA, then hash will match. We will do character by character match, and we will exactly do m comparisons. We will move to next window, again hash will match, again we will do 3 comparisons, again move to next, same thing all the way up to end. So it will be equivalent to the naive approach. Even worse, because we are also doing hash computation. So this will be O of m multiplied by n. But in practical scenarios, you can think these are very limited or corner cases, and for practical purposes you can ignore these, and it will generally work in O of m plus n, which will be much faster than the naive approach.